now that we can use our complex numbers and look at them geometrically, it gives us a different way of writing complex numbers. It's what we call mod-arg form. Mod is just a contraction of the word modulus, and modulus of a complex number is the length of the vector. So now we tie in what we just did in the last topic of vectors and we bring it into complex numbers. So another word we could say for it, I guess, would be magnitude. So modulus is magnitude. So here's our complex number, x plus iy. But I'm saying, hey, I'm going to make it a vector. So I join it up to the origin. The modulus is the length of that vector, or the magnitude of that vector. And so we use that notation for modulus, same as we do for magnitude. We use those absolute values symbols. So mod z. Well, argument is the direction of the vector. So it would be that angle in there. And we abbreviate with arg. So arg z, rather than having to write arguments all the time. And same as we did with finding the direction of a vector, would be the inverse tan of y over x. But with complex numbers, there's a very subtle difference. Notice here I've put capital A instead of lowercase a. If it's capital A, then that angle must be in this particular domain. It must be in between minus pi and pi. And of course, minus pi and pi is the same position. Now, if it's ever in that situation, we go with the positive pi, not the negative pi. So capital A is what we call the principal argument. Little a is just some arbitrary one. That's when I could have 2 pi plus that or minus that, that's fine. I could put anything down that represents the same position. But when it's capital A, they're specifically talking about the principal one. And so we give our answer in between minus pi and pi. So let's go and find the modulus and the argument of this particular complex number. So the modulus, or the magnitude of our vector, would be 4 root 2. The argument, the inverse tan, now I've written it in a specific way. I didn't just say it was -1. I've written it as -4 over 4, so I can work out the position easily. Yes, it is the inverse tan of -1. But if I draw up my picture, right, y is on the top, x is on the bottom. So the y was negative, the x was positive. I'm in the 4th quadrant. So I'm going to give the answer as a negative acute angle. So it'll be minus pi on 4. So I sometimes, if I'm not sure, will actually draw that diagram to the side just to make sure what I'm talking about. But then I can now rewrite every complex number in terms of the modulus and the argument, and it would still define that complex number. So z equals x plus iy. I guess we could now call them the components of the vector, if you like, because we've got in the x in the x direction and y in the... But I could now write it like this, because using trig we could easily work out that x was equal to r cos theta and y is r sine theta. Wow, they're always going to have this common factor of r, so they are modulus, so we tend to write it more like that, r times cos theta plus I sine theta. So the mod-arg form is that, r times cos theta plus I sine theta. There is a notation and a little abbreviation that we can use. Just be very, very careful if you do use it. You'll probably find it's never written in a test. It's never written in solutions or answers. Sometimes in solutions you might see it. Because it's so easy, especially with some of your handwriting, it's so easy to confuse cis with cos. And then you go back and you read your own handwriting, but you confuse yourself. And you go, oh, I'll work out what the cosine of this is, and you come up with a completely wrong answer. So be very, very careful when you're using that cis notation. Cis simply is cos plus I sine. That's all it's really representing there. And so r is the magnitude of that vector, or the modulus, we can now say, of our complex number. And theta is the direction of that vector, or the argument of our complex number. Right, let's go back to 4 minus 4i, because we've already worked out the magnitude. Oh, hang on, let's give it the complex number name. We've already worked out the modulus and the argument. So I could write it like that if I put in cis notation. 4 root 2, the cis of minus pi on 4. Root 3 plus I, okay, let's work out the modulus. It's 2. and argument of z, inverse tan of 1 on root 3. They're both positive. I know I'm in the first quadrant, so that's pi on 6. 2 cis pi on 6. You're going to see these numbers or multiples of these numbers come up a lot. You know, root 3 and that, because they're our exact values. So you tend to find them a lot in questions because, oh, well, nice and neat. You've got a nice exact value we can work out. If I wanted to go back the other way, well, then it is useful to write it as cos plus I sine. I can just go and work out, well, what is the cos of pi on 6 and what is the sine of pi on 6? Multiply out by the 6 that's out the front, and I get 3 root 3 plus 3i. So it's very easy to go in between the two forms of writing our complex number. So playing with complex numbers when they are in that mod-arg form. If I want to multiply z1 with z2, the modulus, I could, again, do it either way. I could multiply them out first, then find the modulus, or I could find the modulus of each individual bit and then multiply the answer together. When it comes to the arguments, though, it's a little bit different. It's a bit like logarithms, in that when we multiply, we actually add the arguments together. So arg of z1 plus the arg of z2 would be the argument of z1 times z2. Now, this brings up, if we go back to what we're talking about here, hang on, this is a vector. Now remember how I said it is actually possible to multiply a vector with another vector? That's essentially what you're doing here when you're multiplying z1 times z2. In this format, you're multiplying one vector with another vector. What effect does it have? Well, the length of the vector, we just multiply the two lengths together. But the actual angle, we're rotating the vector by what we're multiplying by. Let's just prove that, just in case you don't believe me for some reason. Well, I'll let z1 be, and I'll put it into the mod-arg form, cis theta 1 and z2 be r2 cis theta 2. If I was to multiply those two things together, well, the first part's very easy to show because r1 times r2, r1, r2. The other bit with the argument, okay, let's expand out. But if you look at the real part and you look at the imaginary part, we see a very familiar pattern. Look at the real part, cos, cos, sine, sine. Look at the imaginary part, sine, cos, cos, sine. So what we have is the arguments have been added together. The cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And so we have our proof. Now, it logically follows that if you're multiplying more than one complex number together, then we just multiply all the different moduli together, and the arguments, we would just add all the different arguments together. Similar thing happens with division. We can just find the modulus of each individual part, and with the argument we now subtract. Again, very similar to logarithms. When we divide, we subtract. So the argument of z1 minus the argument of z2. I'm not going to do the proof of that one. I mean, it's very similar to the other one. But now it follows. If we've got something like this, well, the modulus, sure, I'll just find the modulus of each individual bit. For the argument, well, whichever one's on the top of the fraction, it'll be positive. Whichever one's on the bottom of the fraction, it'll be negative. So I've got argument of z1 plus the argument of z2 minus the argument of z3 minus the argument of z4. If I wanted to raise a complex number to a power, well, to a power, all I'm doing is repeated multiplication. So the modulus of z to the power of n must be the modulus of z, all to the power of n. What would happen with the argument? Well, if I'm adding every time I multiply, I'm going to be going, oh, argument of z plus argument of z plus argument of z and so on. I'd be doing it n times. So we get n lots of the argument of z. Now, if I want to find the modulus and the argument of this, I no longer have to actually work out what it is. They're not asking for that. They're just saying, what's the modulus and argument of it? So, all right, I'll just find the modulus of each individual bit and then play around with that. Oh, that was nice. 13 goes into 26. We get the square root of 10. The argument for this one's a little bit more fiddly because I don't have exact values. But it'd be the inverse tan of 1 on 5 plus the inverse tan. Notice I didn't write it as a half. I wrote it as minus 1 on minus 2 to remind myself they're both negative. Therefore, I'm in the third quadrant, aren't I? That'll be the third quadrant. So I'm looking for a negative obtuse angle there. And then the last one minus the inverse tan of 2/3. I'm going to have to get an approximation for this one because they're not exact values. I've done it in degrees rather than radians. It doesn't really matter, I suppose. We could do it in radians, we could do it in degrees. But I get this, minus 175 degrees 48. I could then work out an approximation of that answer because that didn't turn out to be a nice, neat, exact number. If that was a nice, neat, exact number, then I could then work out the actual complex number by going, oh, well, it's r cis theta plus I sine theta and calculating that out. What about when we shift the reference point? Now, we looked at that when we're just doing our functions and moving things around the number plane, and now we can use that idea with complex numbers. See, in the Cartesian plane, sometimes we do move our reference point from the origin to somewhere else. The circle, there's a classic example. I've moved the centre to 1, 2. We've shifted it. We can do exactly the same idea in the Argand diagram. Over here, there's Z. Modulus of Z, what does it actually mean? It means what is the length of this vector? Head minus tail, Z minus 0, so at this point it's a position vector, so it's just mod Z. Argument, the direction of our vector, but let's say my reference point is over here, it's some other complex number. Then the length of that vector, head minus tail. So it's Z minus W. So all that the modulus of Z minus W is well, what's the length of that vector that joins W and Z? And the arguments, well, the angle it makes with the horizontal. What direction is that vector going in? 1D. So a little taste of playing with it geometrically.